We're going to talk about error analysis. We're going to review significant figures. We're going to discuss precision and accuracy. We're going to see how that relates to systematic and random errors. We're going to talk about uncertainty, and then we're going to introduce propagation of error. No matter how carefully we perform an experiment, it can never be free of error or uncertainties. In a scientific measurement, the word error or uncertainties mean the same thing. This doesn't mean that you knocked over a beaker or you made a mistake in the procedure. This is something that's uncontrollable. Um, Making a mistake in the procedure is a completely different measurement, okay? Uh, that's not an error or an uncertainty in a scientific measurement, okay? And error or uncertainties is something like the scale is not tailored properly for all the measurements, or during a measurement, a gust of wind comes by, okay? All right. Let's review significant figures. These are going to be important uh, during our propagation of error section. All right, so all non-zero digits are significant. 1, 2, 3, 4, 5, 6, 7, 8, 9 are significant. So that 2, that 8, that 3, they are significant. Interior zeros, zeros between non-zero digits, are significant. So that 0 is significant along with that 0. Leading zeros are not significant. That 0, that 0, that 0 are not significant. Trailing zeros after a decimal place are significant. So that 0, that 0, and that 0 are significant, okay? Zeros before a decimal point, okay, and after a non-zero number are significant. So that 0 is significant. But keep in mind, these leading zeros are not significant. So under these rules, the only numbers that are not significant are these leading zeros. However, there may be some ambiguities that arise. Let's consider this example here, 1,200. None of the rules that we just talked about relate to this 0 or that 0. So we don't know if they're significant or not. So this number would have to be converted to scientific notation. If it's just two numbers that are significant, we would have to write it as 1.2 times 10 to the third. If there's three numbers, then 1.20 times 10 to the third. If all four, then 1.200 times 10 to the third. Okay, 2, 3, 4 significant digits. Okay, try to avoid these. Later, I actually show you an example from another textbook where they have an ambiguity. All right, so exact numbers have an unlimited number of significant figures, so infinite number of significant figures. Some examples are students in a room, chairs in a room, 4 pizzas. Integers in equations, for example, radius is diameter divided by 2. That 2 has infinite number of significant figures. Define quantities. 1 foot is 12 inches. 1 meter is 100 centimeters. Now, don't be concerned that there's no decimal point here. This defined quantity is known in advance that it has an infinite number or unlimited number of significant figures. So I don't need to say 1 meter is 100 centimeters. I can just say 1 meter is 100 centimeters. Okay, so we have these numbers here, and I want you to try to figure out how many significant figures are in each. So you can pause the YouTube video and pause it for as long as you like and try to figure it out. All right, let's try to work this out. So 1, 2, 3, 4 significant figures. 1, 2, 3, 4, 5. This has unlimited because it's a defined quantity. 1, 2, 3, 4. Just one in this number here, just one significant figure. These are leading zeros. These are not significant. And in this number here, again, ambiguous. We don't know this. We don't know those 4 zeros if they're significant or not. All right. Significant figures in calculation. So multiplication or division, we keep the fewest number of significant figures. 4, 5, 2. Okay. So we would multiply this out and then keep 2 significant figures. In addition or subtraction, we keep the fewest number of decimal places. 3 decimal places, 2 decimal places, 4 decimal places. So we keep just 2 decimal places. Okay, so now systematic and random errors. So now these are errors that you can experience in your measurements. Again, these errors are not knocking over a beaker or not following the procedure exactly right. Okay, so an example of a systematic error is let's say the balance is not tiered properly. Okay, maybe it's 1/100th of a gram off. Okay. Another example of a systematic error is the stopwatch running a little too fast. Okay. Random errors are something that can result in a fluctuation of the measurement. Okay. Let's say you have your analytical balance outside and it's a windy day and some breezes are going back and forth, and that adjusts your measurement. Okay. Another random error is human reaction time. Let's say you're using a stopwatch to measure something. Okay. How fast your thumb or finger can hit the stop time, the stopper, is an example of a random error. Okay. Now, what I didn't mention is that a systematic error is something that's inherent in the system. Okay. So precision and accuracy. Often these words are used interchangeably, but they're not. Okay. So accuracy refers to how close the measured value is to the actual value. Okay. And precision is how close the measurements are to one another. Okay, so we've seen these diagrams in our general chemistry books. So this set of bullseyes here are dots here are accurate and precise because they're right on the bullseye. These are not accurate because they're far from the center, but they are precise because they're all kind of grouped together. These are accurate because they're centered around the right number, but they're not precise, okay, since they're kind of far apart. And these are both not accurate and not precise because they're far from the center and they're kind of scattered. We're going to see this again on the next slide. So, again, same thing we just saw. Accurate and precise all bunched together right in the center. Inaccurate but precise. Okay, here they are kind of grouped together, but they're far from the center. Okay, so this is an example of systematic error. Again, like the balance is not tiered. Okay, accurate but imprecise. Okay, so let's say your balance is tiered properly, but you're doing the experiment outside and it's windy. Okay, and in this inaccurate and imprecise, you're doing the experiment outside, it's windy, and the balance is not tiered. Okay, so the non-tearing of the balance will kind of shift the group over here, and then the wind will kind of spread them out. Okay, again, same thing we just saw over here. Here, the random error and systematic error are both small. Here, the random error is small, but the systematic error is large. Here, the random error is large. Let's again pretend it's windy out. But the systematic error is small. Again, the balance is tiered properly. Again, here, the balance is not tiered properly, and it's windy out. Okay, so let's say we have uncertainty in a scale measuring device like a ruler. In your speed of sound experiment, well, you'll be doing a virtual experiment, But if you would have done this in the lab, you would be using a ruler, okay? The smallest increment on the ruler or the meter stick is about 1 millimeter. Thus, the uncertainty in our measurement would be this number divided by 2, or zero point 0.5 millimeters, or 0.05 centimeters. Uncertainty in a digital measuring device is equal to the smallest increment, okay? So let's say we get 4 decimal places for our analytical balance, okay? Then the uncertainty would be in the 4th decimal place, so 0.0001. So how do we write these measurements and uncertainty? And we say we have something called the best measurement plus or minus some uncertainty. Okay, so let's say our best estimate of time is 2.4 seconds with some range between 2.3 and 2.5 seconds. Thus, our measurement would be 2.4 plus or minus 0.1 seconds. Okay? In general, we have the measured value, let's say x, is equal to the x best, whatever the best measurement of our value is, plus or minus some uncertainty. Okay, so this value here, this uncertainty in x, will always be positive. You must always make sure this value here is positive. Okay, because it's always plus or minus some positive value. If it would just flip everything around if it was negative. It's defined to be positive, and the equations are derived such that this is positive. You'll see an example of that at the end. Okay, so how do we state these uncertainties? So let's say we're measuring gravity, the acceleration of gravity, and we know it's 9.82 meters per second squared, but there's some uncertainty in that. Okay, so let's say, or would we write 9.82 plus or minus 0.02385? Probably not, because this uncertainty has much more decimal places than these values here. So we almost always round the uncertainty to one significant figure. And it'll work out that the uncertainty is always in the last decimal place of the value here. Okay, so example, the uncertainty is in the 100th place here, and the last value here is in the 100th place here. Okay? The exception to this is if the uncertainty is a 1, okay? If the leading value is a 1, then in this exception we keep 2 numbers, okay? Why? Because if the uncertainty ends up to be 0.14, throwing away the 4 would be, throwing a large amount of the uncertainty away. Okay. So let's just go over some examples about how to state this. Okay. So we have 2.4 plus or minus 0.3. Again, all of these, well, these 4 have one significant figure in the uncertainty. One significant figure, one significant figure, one significant figure, one significant figure. And these are all these 4 are all, the uncertainty is in the last decimal point of the best value. 10th decimal point, 10th decimal point, 100th, 100th, 10th, 10th, ones, ones. The exception, again, is if the leading value of the uncertainty is a 1. If the leading value of the uncertainty is a 1, we keep the next value also. That would be just again, the logic is that would be throwing too much of the uncertainty away. Okay, so now, let's say we're adding and subtracting values with uncertainties. How do we add or subtract these uncertainties? How do we propagate this error into our final answer? So let's say we have 2 values, A and B. So we have A best plus or minus the uncertainty in A. B is B best plus or minus the uncertainty in B. Okay? So the highest probable value is, and let's say we want the difference, B minus A. So the highest probable value, B best minus A best, would be adding the uncertainties. Excuse me, adding the uncertainties and adding it to B minus A. The lowest probable value is B minus A minus the sum of the uncertainties. Okay, so if our new value is x is b minus a, and recalling that x is x best plus or minus delta a, we see that x best is b best minus a, and the uncertainty is just the sum of these uncertainties. Okay, that makes sense, right? Okay. So this is actually going to give us an upper bounds on the error. There's other ways to reduce the error with, well, we'll see later on. Okay. So let's in our physics classes, we've probably done some conservation of momentum experiments. So we measure the momentum at 2 points in the experiment, and we see if the momentum is the same, then we say, okay, momentum is conserved. But if momentum is different, we generally say that momentum is not conserved. However, we have to remember that there's going to be some error in our measurement. Okay, so let's say we have let's say we measure the momentum before and after some event. Okay, and let's say we want the change of momentum p minus q. Okay, let that be the change, and let p is equal to this value here, and q is this value here. Okay. So if we calculate p minus q, we get minus 0.07 plus or minus 0.09. Let's ignore the 0.09 for a second. If we see a change of momentum of 0.07, we think, okay, so momentum must not be conserved. Okay. However, if we look at our uncertainty is 0.09. Our uncertainty is greater than our measure of the change in momentum, since our error is greater in magnitude than the change in momentum, then our momentum is conserved within our error bounds. Okay. However, if maybe we find that the error was 0.02, then we could say, no, momentum was not conserved within our error. Fractional uncertainties. It's often useful to present the values in terms of fractions. Okay, so to get the fractional uncertainty, we just take the uncertainty and divide it by the magnitude of our x best, okay? And then we multiply it by 100. So say we have the length is 25 plus or minus 1 centimeter, okay? So how do we change this to a fractional uncertainty? Well, we take the 1, we divide by the 25, and we get 0.04. We then multiply that by 100 and express it as a percentage. So the measure of our length would be 25 centimeters plus or minus 4%. The centimeter should be over here. Okay. Sorry about that. All right, so now this looks a little messy here, but it's really not so bad. Let's find the uncertainty associated with multiplying two measured values, okay? So let's say we have our x is x best plus or minus some uncertainty. And let's write it like this. Let's pull out our x best, so we're writing it as a fractional uncertainty, okay? So let's consider momentum again. Momentum is mass times velocity. So here's our mass in terms of our fractional uncertainty, and here's our velocity. So we're just going to multiply these two values here. So momentum, mass times velocity, is m best times v best, and then we're going to multiply these values out here, okay? So that's just, and let's just look at the largest possible value for now, okay? The plus sign. Okay, so we do that, and we expand this out here, okay? Then we just distribute the terms, but one of the terms, this term here times this term here, is a very small value here. So we're going to throw it away, okay? And thus we end up with the momentum is m best, v best, 1 plus this, okay? So again, let me, if you didn't see, if you want me to show you, so again, it's 1 times 1 is 1. This term here times 1 is this term here, okay? Then we have this term here times 1, which is this term, and then this term times this term, which is this term, and we throw this term away, okay? So we just have this term left here, okay? So this is what we have left. I'm going to copy and paste that on the next slide. Okay, so there it is. Okay, I just put little brackets here. Okay. Okay. So again, this would be for the largest, and if we did the same thing, we get a negative sign for the smallest. Okay. So if we compare that with momentum is p best, 1 plus or minus delta p over p best. Okay. We see that p best is just m best times v best, which I'm sure you could guess. And this right here, this delta p over the magnitude of p, has to be this group here, okay? It's actually an approximation because, again, we threw away the fourth term, okay? So basically, for fractional uncertainties, you just add the fractional uncertainties. Okay, let's do an example. Okay, so we have momentum is, so we have these two, we have momentum. We have mass times velocity. And I want you to calculate the momentum and propagate the uncertainty, okay? Okay, so you can pause the YouTube video and try to work that out on your own. Okay, let's show. All right, so P best again is just M best times V best. Okay, so then we're going to just add the fractional uncertainties. We calculate the fractional uncertainty in mass, and it's about 2%. Fractional uncertainty in velocity, it's about 3%. We add those together, and we get the fractional uncertainty in momentum is 5%. Okay, so then if we want it, we could write this in terms of 5%, but if we want it in terms of values that aren't percentages, we take the 5% and multiply it by our P best, again, M best times V best, 4.8. So 4.8 times 5%, rounded to 1 decimal point, is about 0.2. So your value of P is 4.8 plus or minus 0.2 kilogram meters per second. Okay? All right. So I showed this I proved it to you for products, but the same thing is true for quotients also. I'm not going to prove that. So let's say we have some Q, that's some function of a bunch of variables, multiplication and division. If we want to propagate the fractional uncertainties, it's the fractional uncertainty in Q is just the sum of the fractional uncertainties in all the variables. Okay? Great. Here's an example. Let's say I have length 1, length 2 divided by length 3. And here, this is from a textbook, Introduction to Error Analysis by Taylor, 1982. Here he presents presents a number. I know the author is a he because I read the book and the dedication is to his wife. Okay, so here he presents and his first name is James. Here he presents a number, 200, but there's no decimal point. This number here is ambiguous, so there should be, he should have put a decimal point here. All right, so we have this length, and this length. So our measurement for the best L is 200 times 5.2 divided by 10 is 110 feet. Then we propagate the fractional uncertainties. We add them. The fractional uncertainty in the first one, second one, third one, we add them together, 7%. So our final answer is 110 plus or minus 7% times 110, which is about 8. Okay, so that wasn't so bad. But try to work this out on your own. This is an important question. All right. So now let's say we have something, let's say circumference is equal to maybe some value that is an exact quantity, maybe like pi, times something that has an error like diameter. So say C is equal to B times D, where there's no error in B, okay? So all you have to do, you don't even have to remember this. We just have the product of two things. You propagate the error exactly how you've done before, okay? You add the fractional uncertainties, but the uncertainty in B is 0, so this term here is 0, so this makes your life a whole lot easier. Okay, so we just have this term here is equal to this term here, and then we multiply through by C best. Okay, and so we have, again, C best is just B times D best. Again, there's no error in B. With the uncertainty in C is just the magnitude of B times the uncertainty in D. Again, because yes, we had we multiplied through by C. Does that make sense? Yes. Okay. So let's see an example. Okay. So suppose you have a diameter such as a circle. Suppose you measure the diameter of a circle. So you have diameter is 2.0 plus or minus 0.1 centimeters. Use this to calculate the circumference of the circle, including your value, the uncertainty. Okay. So you can pause it here and try to work this out. Okay, so let's see. So again, we know the circumference is pi times d. Okay, so we know pi is, let's say, 3.14. 3.14 times 2. Again, that gives us about 6.3, again, with two significant figures. Again, then how do we get this uncertainty here? It's just 3.14 times 0.1, which is 0.314. And we round that to one significant figure. And in the 10th decimal place, because this is in the 10th decimal point. So we have 6.3 plus or minus 0.3 centimeters. Okay, not so bad. This I'm going to prove to you on another web page. So let's say we have we're almost done. Let's say we have the, let's say we have a function of one variable and we want the uncertainty in this function, okay? So basically what it is the uncertainty is approximately equal to the derivative of the function times the uncertainty in x. Okay, so let's quickly switch web pages. Hopefully my web page didn't close. Good. Okay, so let's say we have, let's say we have a function here, f of x, okay, in red. Now, let's say we have a tangent line at A. Let's just call the tangent line t of x, okay? That's pretty consistent with your calculus book. Let's first get the equation for this tangent line using point-slope form. Remember point-slope form, y2 minus y1 is equal to mx2 minus x1, okay? So the equation of this tangent line is, as a function of some x, is, let's say the second point is some t of x, the first point is f of a, so here, equals the slope of this, that's derivative of f evaluated at a, so that's here, and then x minus a, okay? So then let's add f of a to both sides, so we have the equation for this tangent line is this here, okay? Now, let's get the approximate equation for this f of x, okay? So this approximately equal to the equation for this tangent line. However, the approximation gets worse and worse and worse and worse as we get farther from this tangent line. But if we're really close, then this tangent line approximates this function fairly well. Again, this is called linearization from your calculus class, okay? So now let's just take this equation here and subtract f of a again. And let's say that x minus a is our, this difference here is our uncertainty in x. If that's the case, then f of x minus f of a would be our uncertainty in y. So that's approximately equal to the derivative, let's write it as the derivative of this function evaluated at a. So let's write it as f prime of a, f prime of A. And in my slide, I had, oh, that's not so good, but you know what it is. I had absolute value signs around this. Why do I have absolute value signs around this? Because I always want the uncertainties to be positive quantities. Okay, so that's not so bad. Okay, and we have our expression here. Remember, this is just an approximation, okay, because the linearization is just an approximation. Okay, one more slide. As an example, let's say we have y equals e to the x, and let's suppose we have x at 3 plus or minus 0.1, okay? So let's find the value of y with uncertainty. Okay, so you can pause it and try it on your own. Okay, so what it is just our y best is just e to the x evaluated at 3, which is about 20, okay? And the uncertainty is y is just the derivative of e to the x, which is just e to the x. I picked that for ease. Evaluated at 3, which is again 20, times 0.1, which is 2. Okay, that's it. All right. Hope you liked it.